Hello everyone, I am Ujjwal Bishwas from Indian Institute of Technology, Guwahati, Assam, India. In this work, we propose a real-time interactive visualizer for large classroom to identify overall classroom performance status and students who are in critical state. There are many importance of the classroom visualizer. It aids teachers to understand the impact of their lecture, assists to get fair idea about the students who need help and support to customize the lecture in a better way. Now, why we need a real-time interactive visualizer? A real-time interactive visualizer makes easy to interact and comprehend the real-time classroom status and student location in a large classroom. Also helps to reduce teachers' cognitive load in identifying student performance state. There are many challenges to design visualizer efficient and usable for real-time use. Research studies are inadequate to address the challenges of a large classroom visualization. Limited in showing both the status and location in a small display such as smartphone or tablet. Existing studies have not considered the available screen size and resolution to comprehension of the state at teachers' time and cognitive load. To address the above research challenges, we propose the real-time interactive visualizer. Our visualizer is interactive, renders the classroom status into 2 levels with color codes. Teacher gets to see an overview of the classroom status in the first level. The individual student details are visualized in the second level. We assume the classroom is organized in the form of 2-dimensional matrix. We propose a set of 3 states: critical denoted by capital C, likely to be critical denoted by capital LC, and normal denoted by capital N. Our visualizer consists of 4 separate algorithms. The algorithms are dynamic grid generator, threshold calculator, and dynamic grid coloring, and second level visualizer. Dynamic grid generation takes to input the classroom dimension and the screen height and width. Based on this, it generates the grid dimension. And the threshold calculator calculates the threshold for that particular grid. And grid coloring algorithm use that threshold, and above the threshold grid are highlighted using color. If a teacher tab or click on a particular grid element, it appears the second level visualization. And the second level visualization represent 2 view. One is overview, another one is a detailed view. After every expiry of the interval, it reproduces the threshold and grid coloring. The aim of the first algorithm is to make the grid clickable and distribute the student in equal numbers among the grid elements. The objective of the threshold calculator is to compute a criticality score, compute an elevation factor to manage the number of critical elements, and if the threshold value exceeds the maximum criticality score, we will not have any critical grid elements to display. In such case, we recompute the threshold without any elevation of the average criticality. The goal of grid coloring algorithm is to color assigned to corresponding grid element in each interval. The fourth algorithm helps to render both overview and details of the individual states. Figure illustrates the real-time interactive visualizer. The classroom matrix based on organization of the classroom. C, L, C, and N are the state of the student with the location in a classroom. This classroom organization mapped into grid element using grid generation algorithm. The threshold calculator algorithm calculates the threshold based on the criticality. The red color numbers shows the critical value above threshold. The top 3 grid are highlighted using red color. Remaining are colored with a yellow. Normal grid are colored with a green. If a teacher click on a grid, it appears the second level view. 1/3 region shows the overview and 2/3 region shows the details of the student state. State are indicated by color bounding box with the image of a student. Red bounding box indicate critical student, yellow for LC, and green for normal state student. If a teacher further tap on particular student image, helps to display the student details state. To test the efficiency and usability, we performed an empirical study. We conducted control experiment using a simulated classroom environment. Each class session between 15 to 20 students were participated. We tested efficiency using 12 proposed tasks, and usability is tested using source-based questionnaire. With 12 tasks, these 12 tasks are proposed based on the visualization scheme for the first level as well as the second level, and the both level visualization interface testing, and also identifying the student in a particular zone. We have divided the classroom into a 4 zone here: LF indicates the left front of the classroom, RF indicates the right front of the classroom, LB left back, and RB right back. We collected the teacher's rating on a source-based questionnaire. In this questionnaire, we modified the statement. Simply we use, instead of system, we use the visualizer, and instead of name of the interface, we use during the class lecture. Now we collected the ratings from the teachers. The results and analysis. The first graph is showing the participant versus task completion rate in percentage. The middle, a task completion time in seconds, and the source based scores are in the right. We observed that most of the teachers, more than 50% teachers, completed tasks successfully, more than 90%, and very few, only 2 are equal to 50% or less than 50%, only participant 2 and 4. This shows that our system is efficient to use during a class. Also, for calculating the task time for each task, we found the maximum time required to perform the task between 20 to 25 seconds and minimum of 2 seconds. And we observed that the frequently used tasks like T2, T9, T10, T11 and T12, these are the frequently interested tasks and done with a very few seconds. So this shows that our system is efficient. And the teacher's usability satisfaction, we got minimum of 60% and 90% is maximum, and average approximately 75%. And this source score shows that our system is highly accepted by the teachers. Now in conclusion, our results give a positive indication of the acceptability and the need of the visualizer among the teachers. We observe that system is efficient based on task time, and source scores shows the usefulness of the system among the teachers, and it is possible to use in a smartphone or tab. Further extensive research is required in the direction of the other shape of the class, like semicircular class or circular class. Thank you.